Hi, everyone. I'm Zico. I'm a faculty member here in computer science. Also work a lot in the machine learning department, many other departments actually. And I'm going to talk today about some of the work being done in my group on detecting and adapting to domain shifts in machine learning. This is a pretty popular topic these days, and there's a lot of, I think, really sort of like the kind of the Wild West a little bit in this topic. There's a lot of different approaches that are happening right now. So I think we're still trying to figure out exactly like what we want to be doing. But I'm going to talk about some of the work that we're going on in our group about, particularly this notion of sort of detecting or really evaluating accuracy under domain shift, and then potentially also adapting to domain shift. And feel free to stop and ask questions in the middle. I'd rather this be a little bit interactive than get through all my slides. So feel free to stop me and interrupt. I will have to go pretty closely at 1 though. So unfortunately, I can't stick around too much to answer questions today. I have to head home at 1. So okay, let's jump right in. So I presume many people here probably are, before I start though, I should mention this work really is the work of several of my students and collaborators, and I guess collaborators are now current faculty, new faculty at CMU. So Vaishnav, Christina, Yading, Sachin, Minji, and Aditi are the ones that actually did all this work. And I'm just getting to talk about it. All right. Okay, so let's talk about the problem of distribution shift here. And I assume most people, or a lot of people here might be familiar with this basic setting. The setting is you train your machine learning algorithm on some training set, right? And at evaluation time, you want to evaluate how well this is going to do. And so the thing that we all do is we also draw a separate test set from that same distribution. And because of basic statistics, we know that the performance on our true underlying distribution D is kind of in some sense well approximated by our performance on the test set, right? Because we haven't looked at the test set when we train our model, so everything's good. We can apply basic bounds to get a pretty good estimate of our performance. The problem, of course, is that this is not really how machine learning often works, right? Oftentimes, when you actually deploy a machine learning algorithm, say, going from training it in your data to really sort of using it in practice, you're going to be using it on some other distribution, which I'm calling here like XD prime, and the real world samples in the real world are drawn from some different distribution D prime. I guess there's a good chance people in the last row will miss out on pizza. Now that I think about it, people are getting. We'll see. Is there like a lot left, or is there not much left? Okay. Hopefully, fingers crossed, you get some back in the. You were here first, so I feel kind of bad. That's your fault, right? Okay, now I presume people are sort of somewhat familiar with this, but the main point I actually want to make is that this is not some kind of edge case that we may encounter sometimes in machine learning. This is literally every single machine learning system you will ever deploy in practice, because. Well, I mean, I guess there are some, maybe if like the data is governed by, like maybe AlphaFold is not this case, right? Like AlphaFold, like really governed by physics. That's a protein folding system, really governed by physics. And so it won't, presumably the laws of physics are immutable, and so it won't change. But anytime you have any notion of sort of data collection from the world where people are involved or things happen, this is going to happen. And your data that you evaluate, which actually matters, what actually matters will never match the distribution you trained. This is just a fact of life that we have to deal with. Usually we sort of deal with this by ignoring it and sort of hoping these are close enough to kind of work, but that's really the state of the art when it comes to this. Are we out of pizza already? Are people really not having done it? Okay, good. All right, so what do we do here? How do we actually account for the situation? Well, and basically the question that I want to ask here is, how can we perform well on the world, the real distribution we care about, without going through the process of just collecting more labeled data on the world and running things that way, right? How can we actually perform well in the world using what we have available, which typically is just sort of unlabeled data from the real world? How are we going to do this? Now, I want to start this talk off by being very clear about one thing, which is that this problem actually is ill-defined, right? So this problem is impossible in the worst case always, because I haven't said anything about the nature of the shift that could happen, right? You could change your tasks so that, up is down and down is up all of a sudden, right? And of course, you're not going to be able to perform well no matter how much unlabeled data you have, because the task description just changed, right? So this is, of course, both an ill-specified problem because we don't know, I mean, without some sort of formal constraints on the real world, we don't really or the world distribution, we don't really know what this means to have some new distribution to evaluate on. And I should mention maybe here, as I'll come back to this at the very end, if I get to those slides, which is that what this motivates a lot of people to do is sort of define rigorously the conditions under which we're going to think about drift. So let's think about drift, with a certain divergence between the source distribution and the target distribution, where we bound some sort of distributional measure between these two things. And for the most part, this can convey great insight, but I'm not really a fan of this approach. Because when it comes down to it, I have no idea what a distributional distance over, say, images in the world are, right? What is the distributional divergence between images taken on a car in nice conditions and when it's raining, right? There's no overlapping support whatsoever of these things. The distances are typically, by any reasonable mean, these are not even meaningful distances you can compute here, right? So they're infinite, right? And so this notion of sort of quantifying the types of distributions we're going to care about in some theoretical manner, I think it can provide sort of good insight, and a lot of work like distributional robustness and stuff like this is kind of founded upon this idea. But I actually am much more interested in what sort of techniques really seem to work in practice. Can we improve performance at all in practice? And the reason why I'm interested in this is that the answer seems to be yes, we can sometimes, but we don't really understand why, and we don't really. This whole field has not really galvanized itself yet. And maybe before we even talk about improving performance, let's talk about what seems to be a simpler problem, which is just if I'm given a classifier, given some new data set from some different distribution, but only given, of course, we have labels, you can, of course, evaluate performance, but given only unlabeled data, which, by the way, again, is the realistic scenario, right? You deploy a system, you don't get nice labeled data from that, you get nothing, you just get predictions, you get the data. Can we, just using this unlabeled data, and in fact, we're actually going to use unlabeled data here predominantly, quantify the performance that we expect to see on this new distribution? And of course, just to clarify, I mean, this problem might seem easier, but it's still, of course, impossible, just to emphasize, right? In the worst case, of course, no, you can't. Just like before, you can always just switch the task, and distributions look very similar maybe, but the accuracy can be whatever it wants to be. So there's really no way to do this, I would say, in a truly general sense, because the problem is ill-defined. But what I care about are, there do seem to be many realistic cases where some amount of both these things are possible. And I want to better understand what can we do in those cases and what sorts of techniques might actually work for both these two problems. Okay, so this is what I'm going to talk about today. In fact, I'm going to talk about the second one first. This is based upon two papers by Yading, Christina, Vaishnav, and Aditi, different orders of collaborations. And this follows two papers that look at just trying to evaluate the quality of trained classifiers using only unlabeled data from some new data set. And that's something we're going to care about here. All right, any questions so far? Even high-level ones? I might just defer it till later if it's going to be talked about. But setting makes sense? Okay. Guess I didn't pause for long enough there. Now I put everyone on the spot, I know. So now no one's going to ask. So. All right. Let me jump in and start talking about the second one first, then we'll come back to the third one first. Then we'll jump back up to the second one, and that's going to be actually the sort of the structure of this talk. Okay, so I want to start off actually this. Oh yes, question. Perfect.
So when we talk about distribution shift, we talk about distribution shift where the distribution ends up being not within the like if you have a uniform distribution.
Yeah.
0, 1, within that, like a shift within that, is not as interesting as having a shift outside of support.
Right. So the notion of overlapping support is really kind of sort of I don't know how to wrap my head around this, because the reality is, like, what is support of a distribution when it comes to an image classifier? I really don't know, right? Like in Gaussian data, we can very easily quantify the support. Support's in fact infinite. You can quantify region of probability and say exactly what the overlapping probability mass is. I don't know how to talk about support when it comes to distribution of images. Every image is never going to happen again. They're all measure zero sets, right? And I guess not when you digitize them, but they're all effectively measure zero sets. How are image? I know images are from some distribution in some very vague sense, but in practice, I don't even think of these as distributions. They're just data sets, right? They're just data sets that we have and of a certain kind, collected in a certain way that we want to do well on. This is now getting a little bit on the soapbox here. So when you take your machine learning courses, don't, if that's a learning theory course, don't say like, there's no distributions, it's all just data. Don't say that. They're videos, like they're all point mass distributions. So we have all we actually have. But like, you can train a model on, images of cars driving on, nice roads and all of a sudden, translate it to a different city. And the support is technically zero between the support overlap is zero between two things, but it works sometimes, right? So this is why I don't really like distributions. I like to quantify actual performance of classifiers, right? And sometimes that's what we're going to do here. We're not going to worry about sort of distributional support or overlap or all these things that are key to a lot of the theoretical understanding of these methods. I just want to look at empirical facts that I can verify. Like, what's the performance here? Or as we'll see in a second, if I take two different classifiers, how often do they agree or disagree on predictions? Those are tangible, nice quantities I can wrap my head around, and so I can understand them. I can't understand support actually over the space of images. This doesn't make sense to me. Yeah.
I had a quick question. So are we making assumptions on what is the extent of the
Absolutely not. We're not doing that. So that's the whole point, is that how would you define extent of distributional shift, right? I don't even know how you do it. Like a KL divergence, again, that makes no sense for real data. Obviously then, because we are not making assumptions, these things are going to be empirical facts. The properties I show here will sometimes occur, and then when they occur, you can do cool things. They will definitely sometimes not occur. And then, and honestly, figuring out when they occur or don't occur is in some sense the key question that I think is still open, largely speaking. But what I want to, but just like you can't sort of prove that when a deep network will work, we just still use it. I think what I want to go towards are elucidating properties that seem general enough and reliable enough that we feel comfortable using them, even though, of course, we know this can't always be done in practice, or in theory, it can't always be done. And we can find probably real situations which will actually break it. Yeah, so I'm not going to say assume, D, the KL between D and D prime is less than epsilon. There's nothing like that in these talks. It's going to be much more heuristic and hacky than that. Okay, so the thing I want to start with, so I'm going to talk about that second one first. How do we evaluate the performance of classifiers with no labeled data, right? So on some new distribution, potentially has some classifier. I can evaluate its performance on the test set, right? That I have labeled data from when I connect to my data set, but I have no labeled data on my world set. How do I know how well it's going to work? If we don't have labels, there's only so many things you can do. But when they were sort of working on this, Vaishnav and Yiding and then Christina found this really interesting property, which is that let's take not just a single classifier, but let's take a pair of classifiers. And these classifiers can be as simple as the same exact deep network, just trained with different initialization. So you should initialize the weights differently, right? Some different random seed. seed 1 instead of seed 0, right? Or you just order. I mean, we train these networks with stochastic gradient descent, right? And so we order the examples in some randomized fashion. So maybe we even use the same initialization, but we just order the samples differently when we see them, right? This creates two different classifiers in some sense, right? They're not actually, they seem very, like they should be very similar, but they actually are different, right? They have different weights. They will result in different weights. They will therefore make different predictions, or could make different predictions on new data. Now let's look at two of these. And what we want to compute then is we want to compute on our world data set. So we train them both in their training set with different random seeds. And we take our world. I guess in this case, we have a small amount of data on the world just to validate these things, but in theory, you wouldn't have any on the world. We look at our performance on the world, and we find that, kind of surprisingly, the disagreement between these classifiers tracks very well to their accuracy, or correlates very well with their accuracy. Disagreement correlates with their error, and agreement correlates with their accuracy. And so what do I mean with that? That means if two classifiers on some holdout data sets, this is not the training set, they actually can be from the same distribution or different distribution. Actually, this case, we're talking about the same distribution. So we're talking about a test set, but as if you couldn't observe the labels in the test set. If you take these two different classifiers, but trained on the same training data, and look at how often they disagree on the test set. This quantity will be a very good predictor of their error on the test set. And that's all it is. That's it. That's the secret. And so what I have here are two plots on the right here. And this shows a CFAR 10, a CFAR 100 data set. We take a bunch of pre-trained classifiers. I think someone else in the group trained them. Create a whole bunch of different classifiers with different random seeds and different levels of performance and things like that. I think actually, like, some of them used pre-training, some of them didn't, things like this to get different amounts. Then we would take sort of this whole collection of classifiers and compute their pairwise agreement and look at the average error of those two classifiers that we compared their agreement to. And what I'm showing on the x-axis here is the disagreement, and what I'm showing on the y-axis is their error. And as you sort of see that, this is a zoomed in plot, right? So this is like pretty heavily zoomed in here. There's a pretty strong agreement between these two quantities. And I would say that's actually really surprising. I mean, I think that's actually just totally bizarre, right? Because these are classifiers trained on the exact same data, just on the left with a different initialization, and on the right with a different ordering of the examples. And on new data, they disagree a whole lot, right? Which is surprising in itself. It's like, you think these are going to be super correlated in their predictions, but they're not that correlated. Just the difference in initializations is enough to give them different, some disagreement between those two. And that disagreement corresponds very closely to the average error of any two given classifiers. I mean, so I would think the plots should be like all over here, like in a straight line here, where you have all sorts of different amounts of error, but they're all like really tightly correlated because they all have the exact same, sort of types of data. But it's not. You see this really fascinating linear effect. There's a few questions here, so I'll start with you.
I'm not sure if I understand the question.
Yeah.
So the test error is a property of a specific model. Disagreement is a property of the model request another model.
Yes, two models. So test error. So each point there is two models. The test error plot is the average test error of those two. So you just take their test errors and just average them together. Okay. And then the disagreement is how much they disagree with each other. Yeah.
And like, how are you measuring disagreement?
You take two classifiers. Mm-hmm. You test them on the example. If they make the same prediction on that example, then they agree. Make different predictions, disagree. It's the average disagreement over the entire test set. Yeah. Ooh, lots of questions there. Yeah.
Those points are averaged over two classifiers, right? So do they have like high variance?
They are average over classifiers, and they do have different ones. We typically, I think, in this experiment, average over the orange group and the blue group separately. So they at least were trying to like minimize that, just because they were trained in different ways, those two groups. But yes, there is some variance, but we're tracking, I mean, these things, like, it is the average error what we're tracking here. And so like they're going to have the different errors, but still that's sort of okay. I mean, the conceptual case to have in mind is suppose we train two classifiers different ways, but just because of their nature, they get the exact same. I mean, because like, you know, we train things two different classifiers, they're going to have approximately the same accuracy, right? Like not exactly, but approximately the same. These don't, I mean, they vary a little bit, but like not that much. I mean, no, okay, maybe they may vary a little bit, but like, you know, their variance is not that high. It's I mean, it's sort of ranging between those two extremes, right? Because one is going to have the two low ones, and one's going to have two high ones. So it's not going to be that much difference. Yeah. Yes.
How correlated are the classifiers when conditioned on the incorrect answer? So like of the incorrect answers, how are they correlated at all?
Oh, actually, I think we looked at that. We just look at their, I mean, so obviously if you, that will depend on the number of classes. I believe, I don't know what the confusion matrices look like here of these things. I would think, I'm sure there is correlation, right? Because like CFAR has a bunch of like animal classes and a bunch of like building classes. And so I'm sure it's not like they're picking randomly here. I'm sure there's some correlation, yes. I mean, if it's binary, then whenever they don't disagree, it's the exact same thing, right? So I suspect there's a fair correlation, but we're just looking at like the binary agree or disagree quantity here. Yeah.
So I was wondering what kind of specification of model you use. Like I'd be surprised to know like if flat models are the same as sharp models, right? Like models with flat minima should be relatively more stable.
I don't think this has to do much with the flatness of the model. I mean, we train these models in a bunch of different ways, but we train them all with similar procedures, right? Because we're training them, you know, same. In many cases, we have to try to make them as similar as possible here. To give another rant here also, but I'm very skeptical about the whole flatness of optima and stuff like that as a useful characterization of classifiers. I know people find it very valuable, but we've had a lot of work showing I think that doesn't really matter that much. But this holds amongst pairs of classifiers that can be in some cases very different, and so it seems to be a pretty general phenomenon. Yeah. Yes.
So what was the average error of each of these classifiers like? Were they like fairly accurate in general?
I mean, this is CFAR 100. So CFAR 100, I mean, good performance is probably like 20% error. So these are not trained that well. They're relatively small. We have trained a lot of them. So these are like ResNet 18s, I think. It's fine. It's not great. I mean, that's the error, right? 25, 30, 40. So, but okay.
And my second question is that is there any value to considering like different architectures and different?
Yeah, we do different across architectures. I'll actually come back to that in a second because I think that this honestly is more about we would like conceptually here. The way to think about this is actually two classifiers that are pretty similar, just which happen to have different randomness that makes them different. Right, that's the way you should think about this result here. It's about classifiers that we're trying to make similar, but which, due to stochasticity of SGD or randomization initialization, wind up actually disagreeing, kind of surprisingly, and so therefore wind up having disagreement. I would not try to think here about classifiers being different because then like, I mean, there's also like test error can't be more than a certain amount. There's also weird effects that can take effect there. So think of these, and actually the theory that we have here, and we do have some theory here, which I won't go over, but the theory that we have does initialize does talk about two classifiers that have the same expected disagreement, or sorry, the same expected error, and just are disagree because they are sort of in some sense. Oops. Oh no. See if that ever comes back now. What's the odds? Okay, good. Just because randomization sometimes disagree with each other. Okay, boy, we're gonna get through one slide here. Yeah. I'm regretting saying this. Yeah, good. Go ahead. Let's get through it.
So like maybe I'm missing something, but I don't see what's peculiar about this.
Okay, yeah. Well, why is it peculiar? I would think that if you train two classifiers on the same data, and your only difference is initialization of the weights, I would think these classifiers should wind up being pretty similar in the end. They're trained on the exact same data. Their predictions on some new data set should be super correlated with each other, right? Like they should be like take a non, these are all deep networks, take a non-deep network, take a convex model. You'll end up with the same point. They will make the exact same predictions on new data because they are the same model. They are trained to the same optimum. They are the same model because the model is defined for the training data. What this is saying here, which I think is shocking, is that despite these classifiers being trained on the same data, they aren't that heavily correlated. They are about as accurate with the true label as they are with each other. That's totally bizarre.
But my question was more like test error is the error between prediction and the ground truth. And if that is low, then there will be more agreement between the models.
Sure. So if So there is a region. You can't have disagreement more than like a slope here. So if test error is 0, then of course disagreement is also 0. But disagreement can be 0 while test error is 100.
But they should be correlated. Like
No, I don't think they should be correlated at all. I think I mean, take a logistic regression. They will be incredibly, they will be like the figure will look like this, right? Let me draw on the board here. They'll look like this. If you have these two plots here, right? So this is disagreement, this is test error, they'll be like here. Because you'll have all sorts of different errors, different classifiers, and they'll all make the exact same prediction on a data set. The fact that you have it here, yes, you can never be like this region here. You can't have disagreement which is more than twice the error or something like that, right? So you have to be over here in this region. But you can be anywhere in this region. Why on earth are you on that line? Like that's bizarre. So one more we have.
Okay.
I don't really feel bad for asking questions.
I have two questions.
Okay.
So one is like, I'm curious how this will interact with like model on. So if there are two models that disagree a lot, I guess that the ensemble results would also compared to models that correlate with each other a lot. And in that case, isn't there like a chance that the average will be better?
Right. So okay. So this is a good the combination here between ensembling is really interesting. So the theory that we have, and I'm not going to go into it too much, is that if you think of classifiers that were well calibrated, so well calibrated classifiers means that they sort of know what to know. So they predict that there's an 8% chance this is going to be a dog, then 8 to the time it really is dogs. This is a well calibrated classifiers. It turns out that you can't ensemble well calibrated classifiers because they already have all their uncertainty built in. So basically, ensembling only helps you if there's like if sort of some errors make up for other errors. Right? If everything's well calibrated, you don't benefit from ensembling, which is actually very counterintuitive. People don't really think about ensembling that way. Ensembling kind of works because they're in some sense like uncorrelated, right? And so the case where we know this works theoretically is exactly the case where ensembling doesn't work, right? And it turns out that like, yes, there's like some edge cases here because a few ensembles of these networks do work, but not as well as other classifiers because ensembles themselves of these networks wind up being well calibrated. So they actually themselves have good error. And this does relate to at least some of the theory we have about why these things might work in practice. But those questions are very tenuous there. So I actually don't want to harp too much on those because I think we don't yet fully understand the connections between practical ensembling and like what it means for these sorts of methods. So it's a great connection, but it's one that's sort of not really, I think, fully understood yet. I see. Everyone's saying the same thing. Yeah. When of course, when these things get disconnected, fortunately, I haven't changed slides yet. So, okay. Yes.
Sorry, just a quick question.
Yeah, let's see if I can actually go a whole talk with getting my first slide. Yeah.
People are trained in the same way, right? Like
Yeah, they're all trained in the same manner. Yeah, with the same number of epochs and everything.
if you use like say heavy data augmentation, then the line will be different. Like
Yes. Yeah. Well, no, it doesn't change the line. It changes where you are on that line. So you're better with heavy data augmentation, but you're typically, it doesn't change this fact.
You can improve on your disagreement.
But you improve on your error too. No, you typically you will improve in the same fashion. Like data augmentation does not seem to affect this too much. This still lies in the line. You just improve performance in both directions. Okay. I do want to emphasize here that I actually was not dealing here with the problem that I said I was going to deal with, which is out of distribution data, right? This is actually just evaluated on the test set, on the actual in distribution labeled data. The thing I want to emphasize is that this approach also kind of sometimes works for OOD data too. OOD stands for out of distribution. So what I'm showing here is a data set called the PAX data set. That stands for photo, art, cartoon, and sketch. And this is basically, you have, I think, maybe more than that, around 5 categories of objects, and but done in very different styles. So one data set will be these 5 things like cats and dogs and something like that. But one of the data sets is going to be photos of them, one will be sketches of them, etc. Right? So really different distributions, but there's some dogness that they're both getting at. I don't even know if dogs is in there. I think it might be, but I'm not sure. Okay. So what we see here, I think, is really interesting. Also, by the way, there's some pre-trainings here. So there's without pre-training, you do a lot worse, but you still sometimes lie on this line. So anyway, the point is we do, so the dots here, so the first pick on the left there with the title art, that's the data trained, those are models trained on the art data set. So they're trained on artistic pictures of cats and dogs or whatever. And you find, not surprisingly, on evaluating on art, which are the circles there, you do better than the other ones, right? As you would expect. Now, for other evaluations, so this looks like the upper triangles here. That's when you evaluate, classify, you train on art on cartoons. And what you see is that, not surprisingly, it does a lot worse there. But the amazing thing is that we're still on this line, right? We're still, roughly speaking, on this line. But not always, right? So, look at the cartoon one. There are many cases there where we just don't actually lie on this line here. And so there isn't really much, if we didn't, here we can do this because we have the labeled data, but this is now, we sort of come full circle here, right? We can only make this plot because I can actually evaluate the test error. If all I had in my toolbox was just unlabeled data, I couldn't actually generate these plots. So I wouldn't know if I was in the squares region up there on the right, where you have pretty high error of your classifier, but they're pretty heavily correlated, right? This is what I actually would expect to happen a lot. And you have that sometimes, but other times you don't have it. And there's no way with just unlabeled data to tell which regime you are in. So the way I would phrase this is a first step at sort of understanding the importance of disagreement as a phenomenon, but it's not yet a really practical algorithm for evaluating out of distribution performance. In fact, all the results we have are really just talking about in distribution performance. They're talking about sort of what happens. You have the same, if you have, rather, what happens if you have certain qualities of a classifier like calibration, which we know are violated sometimes out of distribution. So it's a interesting first foray, but I think it's not yet a practical algorithm. So to make it practical, this actually relates to the next work we did, which is this paper called Agreement on the Line. So this is just to clarify, these are the 2 papers again. So this was the paper I'm talking about so far. I was at ICLA this year. This is the next paper. I guess we'll find out tomorrow whether it's going to be at NeurIPS or not. So I can update my slides. But now I want to talk about that second paper, which is going to be a more still worst case, not going to work, of course, but a seemingly more practical way of actually using agreement in a slightly different sense to get a similar thing. Okay, so let me start off by talking about this paper, not by us. I guess Aditi was on the, so she's She's on both of them. So she is doing all this work, but this is a paper that I was not involved with. I know a group of people, Stanford, University of Washington, other places, they observed a phenomenon called accuracy on the line. And this is a really amazing kind of phenomenon, I think. I want to take some time to describe it. If we take a whole bunch of classifiers, so now we're talking about classifiers, and now they'll have different performance levels. So this is not like 2 ones trained the same way that would kind of be the same as you're averaging. Now we're looking at classifiers that are sort of have very, very different levels of performance. And you look at their performance, you plot their accuracy on the distribution that we're trained on the test set, but the in distribution test set versus some performance on some out of distribution test set. Now you're assuming you have the labels here, so you can evaluate both those things. So you have both the in distribution label data, and in this case, the out of distribution label data. Go back to that in a second. But if you do that, you have this really interesting effect called accuracy in the line, which just says that there's a substantial performance drop very often when you move out of distribution. But there seems to be a very strong linear correlation between in distribution performance and out of distribution performance for a classifier, which by the way is a great thing, right? Because what it means is that even though we're not as good out of distribution, continually improving our models in distribution, which by the way happens to be what we spent the last 10 years doing in deep learning, right? Moving ImageNet higher and higher and higher. It could be that we were just overfitting the ImageNet at this point. Certainly possible, right? But I mean, how many papers have been published on the ImageNet? And there's only 50,000 test examples, right? It is absolutely possible that we've just randomly fit. I mean, I know it's like we actually think 1,000 to 50,000, but it is possible that via hyperparameter tuning, via all these crazy optimizations, we have effectively overfit to the ImageNet test set. Definitely possible, right? And if we did that, what would happen is that at a certain point, this line would asymptote, right? Because presumably out of distribution performance on some similar data set would be like a good or as similar as possible data set to this, say, would be like a good indication of how well this classifiers really did, right? So if these things kind of went up for a while and just kind of flattened out, that would mean that after a certain point, we're just overfitting to ImageNet. We're not actually doing any better on sort of other distributions. But in many cases, that doesn't seem to happen. We seem to be doing better and better out of distribution, even though we're not at the same level as our in-distribution performance, right? So this is like, in some sense, kind of justified all the past 10 years of architecture hacking to get better performance than ImageNet. So it was a relieving result. I think they were trying to go for the opposite result when they were trying at the start of the paper, but they found, or predecessors to this paper, they found this result. But the problem here, of course, is the same one. Oh, I realize I'm not getting many chats. Actually, I don't know if you can. Okay, well, I'll do my best. I like to point at the thing, so I'm going to keep pointing, but I'll come back here when I'm speaking. Okay, so the problem here is that to evaluate this line, you still need labeled data, right? To make this plot, you're plotting in distribution test accuracy and out of distribution test accuracy. And there's just no way to actually get that in many cases, right? Like if you don't have labeled data out of distribution, you can't get that. So this is a really interesting phenomenon, but it doesn't actually give us a practical way of assessing out of distribution performance without access to another labeled data set. In which case, by the way, you might as well train on that and just do better on that data set, right? So it's sort of a circular problem here. Okay, so where does this put us? So what we wanted to do is use these similar ideas of agreement to see if we could come up with a more practical way of kind of exploiting this property to actually evaluate performance out of distribution. And the idea here stems from a seemingly very related, but I would actually argue actually quite a priori unrelated phenomenon, which we found called agreement on the line. which basically says that this same effect, same empirical effect, also happens for agreement. So in other words, I take a whole collection of classifiers. Now they actually do get different errors, by the way. So their agreement is going to be their agreement, even though they have underlying very different test errors potentially. Okay, so they have, here we're not actually correlating agreement and error. So this is just plots of agreement here. Take a whole collection of classifiers, look at all pairs in that collection, compute their agreement between each other on an in-distribution test set. That's like the normal test set we have for ImageNet or whatever, and compute their agreement out of distribution on some out of distribution test set, right? Some new data, cloudy data or whatever, right? Like some different distribution. And what we find is two really important things. First of all, those agreements, in distribution agreement and out of distribution agreement, also lie on a line, typically. Not always, but they typically do. But when accuracy on the line holds, when you have this phenomenon called accuracy on the line, right, which doesn't always hold, by the way, there are data sets like this one here, where it doesn't actually hold. It can be violated sometimes. But when accuracy on the line holds, then this property of agreement on the line also holds. I mean, this sounds like a simple statement, but it's actually quite complex, I think, right? So I want to harp on that for a little bit, because I think it's not obvious why this would be true, or even why it's interesting, maybe. But this is the core phenomenon we observed. And the thing I want to actually convince you of, or I mean, make the argument to, is that there's no real a priori reason to think these two should be related. Just like agreement, we could think could be quite differently correlated amongst different classifiers. There's no reason, and not track accuracy very well. In the previous case, there's no reason to think that these things would, like, one would imply the other, or in any kind of formal setting, right? In any kind of formal way. Certainly, you can construct cases where one does not formally imply the other, right? But two really interesting things happen. The first is that it seems empirically. So what I'm plotting here are, and I didn't include the label here. Sorry about that. What I'm plotting here are the pink points, which are a plot of pairwise agreement between two classifiers from our collection, in distribution and out of distribution. And then I'm also plotting in blue the accuracy of those of all the classifiers. So there's going to be more pink dots than blue dots, because pink dots are sort of all the blue dots, all pairs of blue dots. But what you see is that agreement lies on the line, seemingly if and only if accuracy lies on the line. And then maybe most importantly, these lines seem to be pretty similar, kind of the same. The slope and the bias, those linear terms of this correlation, seem to be kind of the same thing, right? This is a purely empirical phenomenon. We don't know why this occurs, but this seems to be kind of an empirical sort of if and only if relationship, right? Where if we have the blue line, the blue dots being on a line is this accuracy on a line phenomenon. When that happens, the pink dots are also on the line. And when the blue dots aren't on the line, neither are the pink dots, right? They're all spread about. And so it seems to be kind of go both ways. All right, so this now, I would argue, makes this whole thing incredibly practical. Because those purple plots that I show you there, like all those purple dots there, that figure I can generate with no labeled data at all, right? Because agreement, out of distribution, in distribution doesn't matter. I can create it with no labeled data. I just have a classifier, have a whole bunch of classifiers, look at their pairwise agreement, look at, compute that over all pairs, and plot it in two distributions. My test set that I actually sort of, was using to develop my algorithm. You shouldn't do that, but that I probably was anyway. And then some new data set I've never seen before. And if they lie in a line, I can estimate the slope and bias of that line and use this as a really simple strategy to evaluate out of distribution performance of my classifier. So that's not merely obvious. Let me just, it's very straightforward, but it still bears in mind some just like what we know here and what we don't know, right? So we believe that if our points lie in a line, then they lie in the same line. Like the accuracy in the line lies in the same line as agreement on the line. So I'm going to use my in distribution and out of distribution unlabeled data to estimate just two parameters, basically, the slope and the bias of that line. Now, if I have some new classifier, some single classifier, and I want to evaluate its performance out of distribution, what do? I just take its in distribution accuracy, right? And that I sort of know because I have a test set in distribution, right? That I can evaluate. Plug in the same A and B I estimated before, and that gives me an estimate of the out of distribution accuracy for that classifier. So again, it's a little bit of a roundabout way of doing things. So you have to sort of kind of know like what you know and what you don't know. You know, I should probably color code these quantities too. You know this quantity here, this quantity here, this quantity here. And all together, you can estimate, you can use those to estimate the missing quantity, which is the out of distribution accuracy because you don't have labeled data out of distribution. Yeah.
Quick question, as a very interesting result, any intuition as to why the slope and the intercept would be the same?
To be honest, this is still the realm of like a weird empirical effect that we don't really understand. We're trying to understand it a bit more formally now in like Gaussian settings. Because again, I started off saying I don't I don't like divergences and stuff like that, right? And the way I put it is, this effect, if it works, is amazing, and it seems to work like surprisingly a lot of the time. Maybe I should just put it up this last slide. But if you just use this procedure to evaluate performance of classifiers, you do in fact do better than other approaches for the same thing. There's two slight variants we have here. This A line S actually is exactly that procedure. A line D uses a little bit more complex procedure for estimating actually kind of all the accuracies simultaneously rather than just one at a time, but it's basically the same thing. As a empirical method, of course, when we know the true answer, so we can evaluate this, when we can evaluate it, this seems to be a very, very effective approach to estimating out of distribution accuracy. However, I think we are now at a point where we have to say, okay, like why is this happening? Can we enumerate simple settings where this does in fact happen? Maybe I'll actually get to that point later in a second. I think we should analyze simple Gaussian cases. That's actually hard because there's no closed form solution for what the like agreement between two linear classifiers on Gaussian data is. It's like some double integral of Gaussian PDFs that ends up being annoying. So I think, I'll talk maybe a little bit more about what's next, but the reality is like this is so far just something that we observe on a lot of data sets, but which has like, if you really want to use it in practice where you can't verify it with any amount of unlabeled or labeled data out of distribution, you have to sort of take a leap of faith there still. Yeah.
Can you say that agreement on the line was an underestimate the practice on the line?
You definitely can't say that. I think I might have picked figures that had that be the thing, but there's definitely no such. Yeah, definitely not. I might have just gotten lucky in those figures there, but no, you could not say that. Yeah.
Say a little bit more about the AB parameters. So I see that most of the lines are below the unity.
Yes, exactly.
Is there any example where it's A is greater than 1 or something?
I mean, so A greater than 1 would mean your out of distribution performance is better than in distribution. That's probably unlikely, right? Like it's I mean, maybe if it's somehow a simpler data set, right? So you've trained on some really hard data set, and then like your test data set are these, perfect pictures of cats and dogs just face on, like exactly it, and then it probably would be, right? So that can be, but that's in some sense a quantification of how hard the data set is, right? This sort of basically is, how further you're, how far below the line you are, quantifies how well does your current classifier transfer to something else. And if it's actually an easier data set, it could definitely transfer and be better. But the most common situation is like you have similar data in some sense, but something's changed. And so then typically for most machine learning, performance goes down. So you're typically below the line, unless you get, really lucky. And then I guess maybe you're sometimes above the line. Yeah.
So the statement here that agreements on the line holds if and only if comparatively with accuracy on the line, right? So I'm trying to reconcile this with earlier example where there's like cat and dog and extension arts where accuracy and agreements are not linearly dependent. So how like is that if and only a statement work? Does that work in that data sense?
Okay, so this data set here, probably shouldn't put this one up actually. It's totally random that those two things are the same slope there. Like they're just these are just like noisy data. They could just be points there. It is bizarre, but sometimes you seem to have this linear correlation anyway. That's not very. Is that what I'm talking about here? This one here, or are we talking something else?
There's an earlier example like slide 2 to 3.
These, right, but this is a different figure. So it's important to note that these are different figures here. This plots disagreement versus error. This one here plots additive distribution versus in distribution performance, either agreement or error, right? So these, I know they kind of like look like someone, but these are actually totally different views of the data, and you shouldn't confuse these two plots. One is disagreement versus error. One is in distribution versus out of distribution. So you can't really, like, there's a third dimension you can't really correlate to. Yeah. There was a question from the chat about sort of using, using some stuff. Yes. So we do know about where he goes now, but yeah, so we do know those papers, and we actually have compared some of them. And I think some of those were like the competing strategies that we show here, or at least there were some. So yes, there is other work in this as well, but the precise strategy here is sort of a different one than what's been in these past papers. Yeah, that was to Kyle's question in the chat. Maybe it was actually even before I started on this section of the talk, even from a while back. So, yeah.
Do you know when the on the line slash the axis on the line is going to work?
No, so there is some theory about like a Gaussian setting where you can show that agreement on the line will hold under very certain kinds of distribution shifts, but even that's very limited, right? And I think actually as a first step, it'll be good to show similar things happen for agreement, but maybe okay. Maybe let me just go to the last one, because I'm not going to have time to talk about the second portion here, and that's fine. I actually like this. This is great, very interactive. Let me go to the last slide, and this is actually my biggest gripe with a lot of this field, is that when I show things like this, people always say, "But when does it happen? What kinds of shift makes these things happen?" And the point that I would argue, and that's, I mean, to be clear, a very valid question. The short answer is we don't know, right? We don't know. However, I actually think the way we should be thinking about these things is a bit inverted. These effects, and the second one from a second, I mean, so I'll put up the slide here, I guess, so just to say, so this, if you're curious about the second part, we do have some methods about adapting distribution shift, equally heuristic, but also seem to work very well. Like you can tune classifiers with just unlabeled data to perform better under shift sometimes, just like these work sometimes, right? But okay, the point that I would make and I would close with is that these effects, to me, actually have to become important characterizations of shift themselves. Okay, and this is actually, I think this is actually the way that we should be going as a field. We should be identifying properties of shift that seem to happen in real settings, and then characterize types of distribution shift, not by KL divergence or Wasserstein distance or things like that, but by this shift is of the type where agreement on the line holds to this degree, or action line holds to this degree, right? So I actually think we should start using these empirical phenomena, or entropy-based test time adaptation. That's the second thing I talked about there. Works and improves performance by this much. I actually think these empirical effects are more valuable characterizations of what we care about with distribution shift. And they are actually quite a bit more tangible than our traditional notions of distribution shift. So if I tell you this procedure will work as long as your KL divergence between these two distributions is less than 0.1, tells you nothing. If I tell you there exists, and we don't know this yet, but where I think we should go with this whole line of work is starting to understand what are the interdependencies between empirical phenomena of different types of shift, right? We seem to have this one here where agreement on the line seems to imply accuracy in the line, under some settings, right? There are a whole bunch of other empirical effects people have found from this disagreement and generalization equality that I showed first. People talk about things like how well calibrated the classifiers are on undershift, stuff like this. These whole things are much more immediately analyzable as quantities. And I think they provide a very interesting kind of notion of a sort of where I would like to see us going is sort of creating like a dependency graph between all these empirical phenomena, because they're all very useful. If we know these things hold, we can do certain very useful things. They seem to be very important characterizations of the drift itself, right? Does the drift satisfy this or not? This one clearly does. There's something clearly different. Sorry, I'm going through all my old slides, other slides now. There seems to be something very different about this drift than that drift. And I would actually hazard to say that what I think is important as the difference is this plot. That is the difference, or at least a valid way of visualizing that difference. So when we ask when does this work? It's a completely valid question to ask. And we should and we are doing some of the sort of theoretical analysis to say, okay, yes, in this Gaussian setting it will work. That will hopefully give us some additional insight. But I think we should never start there, because if you start there, then all you know about is about Gaussians, and you don't get very far. I think where we should start are effects that, if they are true, are very useful, because we can leverage them to either understand our performance or improve our performance. And if we start there and use those effects to quantify the kinds of drift we see and all understand their interdependencies and what implies what, et cetera, we'll wind up with more and more certainty. Very similar to deep learning. We just kind of trust it because it works on different settings. If these things start working everywhere, we will gain trust in them and we'll use them more and more. And this, to me, should be the agenda, or at least a major part of the agenda of understanding how to practically cope with distribution shift. Okay, so I think I'm going to end there. Great discussion, actually. I really enjoyed going through this in some detail. Hopefully, because I went through this, everyone sort of got at least the nugget of information here, which may have been missed had I gone through the slides. I think I've done these same slides in 10 minutes in the new student orientation for MLD. So hopefully the people that are there actually understood it this time. I think, as I said, this is all of machine learning. I think dealing with this problem is one of the key practical challenges to machine learning. And so approaches that can make this better, again, in practice. And I also realized saying in practice, but then showing things also some data sets like CFAR C and stuff like that is not really valid, but forgive me for that if you know what that means. The more we can push toward things that quantify the real shifts we see in the world and that are useful there, I think the better. All right, thanks very much.